So yesterday, we talked about proofs. We did some proofs. We even did some complex proofs. We talked about how in an isosceles triangle, the altitude, the median, and the angle bisector are all the same thing. And so today we're going to do some more proofs. We need a little more practice. Proofs are really, really important. So I was sitting and trying to think of what proof we could do. I was drawing a bunch of circles because I'm a math teacher and waste my time drawing circles and chords and fun things like that. I drew a circle and I drew these two chords and I realized that there's a property about this it's a good proof because it uses a lot of properties of circles. And the proof is that if I have two chords A, B, and C, and D, that as long as the chords are congruent and they're in the same circle, this is very important, this doesn't work for two completely different circles. If it's in the same circle or if it's in a congruent circle, that these two chords are going to be equidistant from the center. And I can show you that it's true with this specific and particular circle, my handy-dandy measuring device. Put one end on the chord and one end on the center, and that is that distance. And do the same over here, and it's the same distance. So we know it works for this circle. Okay, well it works for this circle, so it works for every circle. We're done. Okay, let's all go home now. We need to prove it. We know it works for this circle. Does it work for all circles? Well, let's set up our proof. Take a second, write it in your notes. So we have a circle, WUOM, our points on the outside. It's circle R. We have WUOM. Two chords WU, chord O and M. And we are given that the two chords are congruent. So we're given circle R, and WU is congruent to OM. Now we need to stop for a second. We need to talk about what does it mean for a chord to be the same distance from the center as another chord. How can we measure that? That could mean a bunch of things. It could mean that the farthest point on the chord is the same distance from the center of the circle as the farthest point of the chord on the other one. But when you think about that, that really doesn't make any sense whatsoever. Because I could have a chord right here, which is clearly not the same length. But this distance and that distance are the same. They're both radii. We know that all radii within the same circle, or congruent circles, are the same distance. That's basically by definition. So clearly that measure of distance is the wrong one. What other ways can we measure this? How about the shortest distance? If we take the shortest distance between R and, we'll call this point X, and the shortest distance between R and point Y, and if we can prove that that and that are the same, that Rx is congruent to Ry, then we can safely say we've proven that the chords are equidistant from the center. So what we have up here proved, W, U, and OM, we can restate this as saying prove Rx is congruent to Ry. It's the same proof. It means the same thing. We're phrasing it slightly differently. So how do we do this? Well, what do we know? What are some proof strategies we have? We can construct things. We can try and make some triangles, maybe. Triangles are very helpful. Let's get some triangles on here. What triangles can we make? Oh, we can make any triangle we want, but there are specific triangles we want. For instance, this triangle. Triangle R, W, and U. And while we're at it, we'll do this triangle. Triangle R, M, and O. And we know, because they're radii, that RU, RO, RM, and RW are all congruent. They're all radii of the circle. Let's not forget what we're looking for. We're looking for X and Y. We're looking to make sure that this line is congruent to this line. Well, let's see what else we can do. What else do we know? We know we are given that WU is the same as O and M, which means this line and this line are congruent, which means those triangles are congruent. Do you guys see that? Because of side, 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 those two triangles are the same. So we have triangle ROM is congruent to triangle RUW by side, side, side. We also know that they're isosceles triangles. Triangle ROM, triangle RUW, isosceles. Why? Well, by the properties of an isosceles triangle, the sides are the same, so they're isosceles triangles. Let's say definition of isosceles. Well, that also means that these angles are the same, and these angles are the same. And more than that, since the triangles are the same, by CPCTC, if you remember from yesterday, all four of those angles are the same. So we have angle M, angle O, angle U, angle W are all the same. CPCTC and isosceles. Now this is an altitude. We actually constructed it as such because we wanted the shortest distance, and the shortest distance is going to be the straight line between, it's going to be the altitude. We have an altitude of two isosceles triangles. You can take it in any one of 5 or 6 different ways, but it boils down to this is congruent to this because they're the same part of congruent triangles, which means by CPCTC, they are congruent. Which means Rx is congruent to Ry, CPCTC, and that's exactly what we're trying to prove. So there you go. Any questions? All right, guys, work on your homework and have a great weekend.